Welcome to this explainer. If industrial chemistry suddenly stopped tomorrow, the modern world would literally grind to a halt within days. There'd be no synthetic fertilizers to grow our food, no batteries to power our devices, and absolutely no refined metals to build our infrastructure. It's an incredibly high-stakes game. What we're really talking about here is a massive balancing act of chemical yield, reaction rate, and economic cost. Today, we're going to dive right into the giant chemical puzzles that engineers have to solve every single day just to keep society running.
So you might be wondering, how exactly do scientists manage to cheat nature's rules? To mass-produce the highly specific, complex chemicals that keep our global population alive, chemists basically have to manipulate environments in some pretty extreme ways. It's honestly like pulling off a microscopic grand heist. You see, molecules are fundamentally lazy. They naturally just want to reach a stable, resting state and hang out there. By forcing them to react and do things they have absolutely zero desire to do, engineers are manipulating nature on a scale that is kind of hard to even comprehend.
And to give you an idea of the sheer scale we're talking about, just consider this staggering statistic. About 90% of the world's sulfuric acid is made using just one of the processes we're going to talk about today. Sulfuric acid is so crucial that it's actually considered the ultimate benchmark of a nation's industrial strength. The more of it a country uses for things like battery manufacturing, fertilizer, and wastewater treatment, the stronger its economy is. So yeah, the human stakes behind these chemical equations are absolutely immense.
Here is our roadmap for today. We'll start with the rules of equilibrium, move into Le Chatelier's balancing act, then break down the Haber process and the contact process before wrapping up with the industrial compromise. Let's get right into it. All right, kicking things off with Section 1, the rules of equilibrium. The absolute biggest hurdle in industrial chemistry is that a lot of these crucial reactions are reversible. That means once you successfully combine your raw materials to make this highly valuable product, that product can stubbornly break down and revert right back into the original reactants. When the forward rate of making your product perfectly matches the reverse rate of it breaking apart, you've hit what we call dynamic equilibrium in a closed system. At that point, the total amounts of reactants and products just stop changing. Think of it, well, it's kind of like running up a down escalator at the exact same speed the stairs are falling. You are expending an incredible amount of energy, but you're getting absolutely nowhere. And for a manufacturer who's trying to make as much product as possible to sell, this chemical stalemate is obviously incredibly bad for business.
Which brings us to Section 2, Le Chatelier's balancing act.
This is essentially the ultimate rulebook for breaking that chemical stalemate. Le Chatelier's principle is basically nature's way of fighting back against any change we try to impose on a system. It states that if a dynamic equilibrium is disturbed by changing the conditions, the system is going to intuitively respond to counteract that change. It's exactly like a seesaw. If a chemical reaction is exothermic, meaning it naturally releases heat as it moves forward, the reverse reaction will always be endothermic, meaning it absorbs heat. So, if we deliberately try to crank up the temperature on the factory floor, the system forcefully pushes back by favoring the endothermic side just to absorb that extra heat. Conversely, if we rapidly cool the whole system down, it shifts the balance right back toward the exothermic side, desperately trying to replace the heat we just took away.
And the exact same rule applies to pressure when we're dealing with gases. If we increase the pressure, essentially squishing the entire system into a dramatically smaller space, the system fights back. It shifts the equilibrium toward whichever side of the equation has fewer gaseous molecules, naturally bringing the pressure down. Imagine trying to stuff 20 clowns into a tiny compact car. Eventually, the pressure builds so high that the car doors are just going to want to pop wide open to relieve that stress, right? Well, chemistry works the exact same way. Knowing how to expertly manipulate this seesaw is the true key to industrial chemistry.
Moving on to Section 3, the Haber process. Let's see how this actually plays out in the real world with the Haber process. This is the incredibly famous industrial method used to pull nitrogen directly from the air and hydrogen from natural gas, just to synthesize ammonia. First, they source 1 molecule of nitrogen gas and 3 molecules of hydrogen gas. Next, they compress these gases to a staggering 200 atmospheres. To put that into perspective, that's a crushing, violent pressure roughly equivalent to being thousands of feet deep under the ocean. Then they pump him into a massive tank filled with layers of an iron catalyst at 450 degrees Celsius. Finally, the newly formed ammonia gas is cooled down until it liquefies, allowing it to be safely drained off, while the unreacted gases are recycled right back into the system. Notice the math here, though. 4 total reactant gas molecules are being forcefully squeezed down into just 2 molecules of our ammonia product.
Because 4 molecules are turning into 2, the Chatelier's principle tells us that applying high pressure will force the equilibrium to the right, giving us more ammonia. So,
The obvious question is, why stop at 200 atmospheres? Why not crank it even higher for maximum product? Well, 200 atmospheres is a massive compromise. Pushing the pressure any higher means you have to build incredibly thick, specialized pipes and run these massive, power-hungry compressors. Plus, you introduce a terrifyingly high risk of catastrophic failure. The cost of all that electricity, combined with the deadly risk of an explosion that could level an entire facility, far outweighs the profit from squeezing out just a tiny bit more ammonia.
Now we run into a really fascinating contradiction in the engineering. The synthesis of ammonia is an exothermic reaction. It releases heat. So according to the seesaw rules we literally just talked about, lower temperatures should absolutely favor the production of ammonia. If freezing cold temperatures yield the absolute most product, why on earth are they running the reaction tank at a scorching 450 degrees Celsius?
The answer? Because time is money. Yes, a freezing cold tank would theoretically give you a chemical equilibrium with a massive percentage of ammonia, but the molecules would be moving so incredibly slowly that it could take years for the reaction to actually happen. Imagine a factory owner sitting around for a whole decade just to get a single measly barrel of ammonia. It would be a total economic disaster. Manufacturers need to produce tons of ammonia today. So 450 degrees is the perfect economic sweet spot. You get a slightly lower total yield of ammonia, but you get it fast. And to speed things up even further without messing with the equilibrium, they use that iron catalyst we mentioned. It provides a chemical shortcut that dramatically lowers the activation energy needed to get the reaction going.
That brings us to Section 4, the contact process.
While the Haber process makes ammonia for fertilizers, the contact process is the beast used for the mass production of sulfuric acid. As you can see, it's a continuous, roaring flow. On the left, a giant furnace burns a high-pressure spray of molten sulfur in perfectly dry air to make sulfur dioxide. That extremely hot gas then moves into the catalytic converter, right in the middle, undergoing a critical reaction to become sulfur trioxide. Finally, it moves into the towering absorber on the right, where it'll eventually be converted into highly concentrated sulfuric acid.
Let's look at those stages just a bit closer. After making sulfur dioxide, the main hurdle is oxidizing it into sulfur trioxide. Then comes a very careful, incredibly perilous step. You'd logically think they just add water to the sulfur trioxide to make sulfuric acid, right? Actually, doing that immediately creates a highly dangerous, uncontrollable, and severely corrosive fine acid fog that is nearly impossible to condense safely. It would literally dissolve the equipment and severely endanger everyone in the plant. Instead, they carefully absorb the sulfur trioxide into pre-existing sulfuric acid to make a thick, heavy liquid called oleum. Only then is the oleum safely and slowly diluted with water to seamlessly yield twice the amount of concentrated sulfuric acid they started with.
Now, let's look at the conditions inside that metal converter tank. Just like the Haber process, the contact process converts more gas molecules into fewer gas molecules. 3 moles of reactants form 2 moles of product. So again, higher pressure should theoretically favor the yield. But here is the surprising twist. They run this massive industrial plant at just 1 to 2 atmospheres of pressure. That's barely above normal room pressure. Why? Well, because at standard pressure, the equilibrium already sits at a phenomenal 96% yield of sulfur trioxide. In the industrial world, 96% is essentially an A+. Spending millions on heavy-duty equipment and massive compressors just to chase that final elusive 4%? That's a complete fool's errand. It's simply an unnecessary expense.
And just like our first puzzle, this reaction is exothermic, so they use a compromised temperature of roughly 450 degrees Celsius to make sure it happens fast enough. But here, they use a totally different catalyst, layers of vanadium 5 oxide. Remember how the iron catalyst provided a shortcut earlier? This specific vanadium catalyst does the exact same thing here. It provides the perfect surface to speed up both the forward and backward reactions equally. It gets the plant to that highly profitable 96% equilibrium state in a fraction of the time, bypassing the need for extreme, sustained heat and saving immense energy costs in the process.
Finally, Section 5, the industrial compromise.
When we put both of these massive chemical puzzles side by side, we see these striking, shared themes that practically define modern industrial chemistry. Both the Haber and contact processes require a precise compromise temperature of right around 450 degrees Celsius. Both completely rely on the presence of a highly specific catalyst, iron for ammonia and vanadium V oxide for sulfuric acid. And both require incredibly precise calculations regarding pressure to find the exact sweet spot between a high chemical yield, a blistering reaction rate, and safe economical operating costs.
Now, we always want to ground this science in why it actually matters to our everyday lives. These high-stakes compromises aren't just academic exercises on a whiteboard. They literally revolutionize global agriculture and industry. The ammonia produced from the Haber process provides the synthetic fertilizers required to grow our food. It's actually estimated that the nitrogen inside the proteins of half the human bodies on Earth right now came directly from this specific chemical process, half the global population. Meanwhile, the sulfuric acid from the contact process is the invisible backbone powering our modern manufacturing industries. Without these precise chemical compromises, the modern world as we know it simply wouldn't exist.
But, we also have to look forward. Running massive furnaces at 450 degrees and powering giant compressors to reach 200 atmospheres demands incredible amounts of energy, which contributes heavily to global greenhouse gas emissions. Scientists today are relentlessly searching for alternative catalysts that could work efficiently at much lower temperatures, like maybe 300 degrees, which would drastically reduce energy costs and shift the chemical equilibrium even further in our favor. So I'll leave you with this thought. As our global population continues to grow, can the next generation of chemists discover new ways to sustain our world without costing the Earth?